So to continue with section 4. Now, we've actually already talked about a problem like this before. Okay, finding vector components. This one, honestly, I always default back to the old way, as long as you understand where things are coming from. The last part of the section actually deals with what are called projections. That's when you take one vector and fit another vector and figure out the parts of the first vector that apply to the direction of the second. So you basically throw out anything excess. Well, technically that's what you do with this problem. Where you have a boat on a ramp, the idea is you can actually do what's called decomposing a given vector, pulling out only the pieces you care about of a given vector and change it into the sum of two vector parts, two vector components. Okay? So the idea is if I have the force for this, your boat pulling out of the water, so the weight of the boat and the trailer together generates this force due to gravity. Okay? So you have two different things of actual work going on that are vectors as well. You have the boat being pulled back down into the water. I actually usually draw this one the other way. It doesn't honestly matter. Because ultimately, what part of these vectors do we care about? Do we care about their direction, really?
No.
We care about their what? Magnitude. So it doesn't matter if you're going up or down with these things, whether it's positive or negative. I only care about its magnitude. So the idea, they draw this one going down the ramp instead. It's the same idea, though, as well as the vector that represents the force of the boat and trailer against the ramp, perpendicular to the ramp. Okay? Now these two things together, what they do with this is if you add that W1, the amount of trying to pull back down the ramp, versus the amount going against the ramp, add those two up, you get that force vector. Well, if you look at this visually, that's what happens. If I take W1 and move it down to here, W2 plus W1 generates that force due to gravity. Okay? It's a weird way of thinking about it, and that's why I don't like doing it this way, but that's where this stuff leads in the second half of this chapter. Okay? And they'll usually do that as a negative component too that's pulling against, and they make force due to gravity a negative since it's going down. Okay? A lot of that's so counterintuitive that I try to avoid it, but it does lead into this idea of projections. Okay? So, the idea is if I have two vectors u and v, okay, u is some combination of two other vectors added together. So if I take W1 plus W2, those added up would give me this vector u. Okay? That's that resulting vector stuff. Now, W1 and W2 are orthogonal to each other, which means what again? Perpendicular. They meet at a 90-degree angle. Okay? So, because of that, I also have W1 is parallel to vector v. Now, the nice thing about vectors, when they're parallel to each other, what does that actually mean? Because vectors are movable. Well, not quite. It's not that they're equal, because their magnitude's not the same, but their what is? Direction is the same. So because you can move them wherever you want, you can actually lay them right over top of each other. So W1 and V, if they're parallel, which is what this says, that means they're over top of each other, but they're not necessarily the same length. So they're scalar multiples of each other. Because they're on the same, going the same direction, so if you lay them on top of each other, one's just longer than the other. That's what that's saying. Okay? So vectors W1 and W2 are what are called vector components of U. Because if you add them both up, you get U. Okay? W1 is also what's called a projection. And they'll use this notation for it. A projection of vector U onto vector V. What that actually means is, if I go to vector U here, I just had U. I want to figure out this W1. If I go straight perpendicular down to vector V, so if I extend vector V, wherever that hits, that's the projection. So a scalar multiplier. So you either extend or shrink that vector V until it hits that altitude, that height of the triangle. Okay, and you can even go the other way with it. If you have that obtuse angle there, you could go backwards, in other words, parallel scalar multiplier of V, and bring that vertical down. Okay? It's a little bit strange to think about, but what the idea is, they're splitting that up into only the component that you care about to match up to V. Because V, the way they draw this, is completely horizontal, right? So do I actually care about the vertical component of U at all? as far as v goes? No. So the idea is they eliminate the vertical component. Well, what that does is drops u down, so it has the same relative endpoint, but without caring about the vertical. So it drops it down to the same line as what v is, in this case horizontal. So what it's really caring about is the horizontal component of what you add together to get u. Well, you add w1 and w2 to get u. So that's what they call a projection, when they drop that down onto wherever v is. Okay? Equation-wise, it looks a little bit weird, and this is the kind of the thing we avoid for the most part, but it does apply. You need to worry about it when you have weird vectors. If they're putting easy vectors at you where one of them's like on the x-axis, there's shortcuts I'll show you in a second. If they have two vectors that aren't on nice values like the x or y axis, then you use what's called the projection of v onto u. Well, actually it's just the dot product of the two divided by the magnitude of the whatever you're projecting onto squared times the vector v. Well, everything in parentheses there is going to generate what kind of value? Is this going to generate a vector? Ignoring the v here, just the parentheses. No, generate what? Yeah, a multiplier, a single number. Okay? So all that just comes out to be a single number, and then you're going to multiply it times v. So if I have a vector like this, I want to find the projection of u onto v. So I'm going to draw this real quick. Okay? 8, 2 is I'm going to go out 8 to the right and 2 up. So that's going to be about here. So this is the vector v. Okay? The vector u is 3 and 4. So over 3 up 4. So that's going to be about here, roughly. So there's your vector u. Now if I want the projection of u onto v, what that means is I just want the component of u that's along that line v. Well, the idea here is if I went along this line, if I drop an altitude perpendicular to v down, and then draw a vector along that stops where that altitude is. This little portion here, that's your projection. Okay? Well, the nice thing, that would be really weird to figure out. So what I do instead is use that projection formula. This is equal to the dot product of those two vectors divided by the magnitude of v squared, all that times the vector v. So it's modifying the length to be appropriate along that vector v, and then it's multiplying it times the vector v to change those values. So mathematically it's not too bad. It's weird conceptually, but what's u dotted with v? If I dot u and v together there. If I dot these two vectors together. Remember how to do the dot product? You multiply the components and then you add them together. 32. So you get 24 plus 8, so you get 32. Everybody vaguely remember that from Friday?
Vaguely.
Okay. On the bottom, I'm going to take the magnitude of v and square it, what I'm projecting onto. So what's the magnitude of v? Square root of 68, except for I'm squaring that, so 68. Now that's going to be times the vector that I'm projecting onto, that 8, 2. So 32 over 68 is? Simplify it. What do you get? 8 over 17. Take that times the vector 8, 2. Use 64 over 17. And 16 over 17. So if you think about that for a second, what that's saying is, let's see, what would that be? Almost 4 divided by a little bit less than 1, right? Or not divided by, and a little bit less than 1. So that's what this is here. It's going over almost 4 and up almost 1. That's this red vector here. Okay. Does that make some sense? Because it's not going to make perfect sense right now. It is a convoluted concept. All right. Now, what this next part's saying, write u as the sum of two orthogonal vectors. Well, the two orthogonal, in other words, two vectors that are perpendicular to each other, are these small ones here. On that previous page, they listed those as W1 and W2. If I add those two together, that gives you U. Well, this W1, that is your projection. So you can write that as projection of vector V, or vector U, sorry, onto vector V, plus W2. Now W2, that is your altitude from U down to V. Okay? Add those up, you get vector U. That's what that part's talking about. So that W1, the part that's exactly parallel or on the line of V, that's the projection of U onto V. The one that goes from there, altitude up to vector U, that's that W2. Okay? So when you're doing a problem like, yeah, so if you subtracted them, you get the projection. So when you're doing a problem like this, where it's a truck on a hill, 10 degrees incline on the hill, okay, draw some point of contact, so there's a wheel. Don't care about the rest of it. Since I'm not worried about friction, I don't care about the rest of it. 36,000 pounds is the gross weight of the trailer. So what direction is that force being applied? Straight down. So from here, the magnitude of this line would be 36,000. Okay? So the magnitude of that line is 36,000 on a 10-degree incline. I want the force required to keep it from rolling back down the hill. Well, that's this here. I don't know how long that line is. I don't actually care how long that line is yet. So I want to look at, since I have this relationship where it's perpendicular here, I'm going to cheat. I'm going to draw a line that's perpendicular to the hill here. Now, I don't know how long this line is. Okay? But what I want to do is generate the projection of it. So I want to go, or I should say of this one, in that direction. So I want to go exactly altitude down to that. It's the same thing as the projections. Now, I don't do this with projections, but that's how the relationship is, okay? What I actually care about is only up to this point, because this parallel line here and here need to be the same length. The magnitude of this line is your amount of force to keep it from rolling back down the hill. So this is a projection problem, but we don't do it with projections. I'm not saying you don't have to do it with projections either. Okay? I just want you to see how they're related to each other. Okay? Because if I did this without projections, well, what other piece of information do I have about this triangle? Yeah, the small angle up here, because you have two crossing sets of parallel or perpendicular lines, this would also have to be 10 degrees, just like this is. And then I care about this magnitude here. I don't care whether it's positive or negative, I just want that length. So what would I do? Yeah, I would just use SOHCAHTOA. That's opposite and hypotenuse. So sine of 10 is equal to the opposite over the 36,000. Yep. So what's x? So 6,251 pounds, approximately. Okay? Now I can do this with projections, but what I would have to do is actually figure out the projections for the force of gravity. That one's easy. What's projection for the force of gravity? Or not projection, vector for the force of gravity, sorry.
0, negative.
Yeah, 0 and negative 36,000. And then figure out for this here. Well, this one is just, well, it's a little bit weird because of the angle on it. But I can actually just treat it as, let's see, what would that be? 300 and, or no. Around would be 280 degrees. So I don't know the length of this. So what I would do, it would be just cosine of 280, sine of 280, because what's the length of that? 1. But I can extend that with the projection. So I project this onto this, drop that down. Doesn't matter how long I make this. I can leave it as just 1 unit long. To me, this is easier, but that does work. In your book, we'll do it with the projections just so you can see it. If you want to do it this way, do it this way. Okay? Questions on that? Okay. Now, one other thing. We're also going to look at the amount of work done. Because the work's not too bad if all your force is being applied in the exact same direction of travel. Okay, going back to basic physics, work is going to be how much force you're applying over the distance traveled. You just multiply those two numbers together. That's though if I have something over there and I'm pulling it directly at me. You don't always do that though. Okay? If you're pulling something along direction but you're pulling at an angle up, well, that angle up doesn't affect the horizontal movement. So what they again do is a projection. They take this value and project it down onto that direction of travel. Okay, but there's shortcuts for this. I don't bother with this because I can also cheat. I can just take the cosine, because if this only works though if you're traveling horizontally. If the object is traveling horizontally along here, well, you only care about the horizontal component of this vector. This vector is made up of cosine of theta, sine of theta. You only care about the cosine of theta part of it. Take that times your magnitude, takes that times the magnitude, in other words, the length from P to Q. It's the same thing as the projection. It bypasses all that because you do not care about the vertical. You only care about the horizontal. Okay, so you can do that either way. And also, because of that, you can also just change this. If you have your work done along, so moving along that vector PQ, you can actually just change it into a dot product. You can just take the vector F, that force being applied, dotted with PQ. Because if I look at a problem like this, if I want to slide an object around along the floor, right? Person pulling a rope with a constant force of 25 pounds at a 30-degree angle. Find the work done if the object's dragged 40 feet. So the 40 feet here is from P to Q. You're dragging the object here. Well, what's that as a vector? 40, 0. So if I take the dot product of 40, 0 with whatever this is, what's going to happen to the vertical component?
It's not important.
Why?
It's horizontal.
But mathematically, though, what's causing it to be unimportant?
Because we're only going horizontal.
Right. What? The 0. Because you're going to multiply times 0. That vertical part will get multiplied by 0. So if I write this one, now this is a 25-pound force at a 30-degree angle, right? So what is this one as a vector? Say again? Yeah, 25 times that cosine 30 sine 30. Now I'm going to dot that with the vector 40, 0. And what ends up happening is you have 25 times cosine of 30. The sine part, or that times 40, when you dot those together, plus, well, who cares, times 0. Right? So what's 40 times 25 cosine 30? Well, you got a calculator, use it. Dot them together, what do you get? 866. Now, the harder question, what are the units?
Pounds per feet.
Foot-pounds.
Pounds.
There's actually a term called foot-pounds. Because if you look, this up here, the magnitude of this thing is the number of pounds. This is feet. Multiply together, you get foot-pounds. It's often written like that.
What is it not often with?
Well, honestly, in physics, what do you usually use for work instead of foot-pounds? Newtons.
Like fictions?
Or wait, no, work would be joules. I'm sorry, yeah. Force is newtons. Work would be joules. Yep. Questions on any of it? This is a more convoluted section. It's got a little over 10 minutes left. Spend some time on it. If you put this one off and then deal with 3-5 tomorrow and, oh yeah, I need to look at that before the test Sunday night, you're not going to have a clue. Get to work.